Hello everyone, welcome back to MathX. I am Dr. Sovan Bera. In today's video, we are going to solve a very important CSIR NET February 2025 linear algebra questions. We will discuss the concept of diagonalizable matrices using simple method, shortcut tricks, and detailed explanation that are useful for CSIR NET, GATE, IIT JAM, University examination. So let's start it. Let A and B be 2 by 2 matrices with real entries and M equals to AB minus BA. Let I to denote the 2 by 2 identity matrix. Which of the following statement are necessarily true? A. If A and B are upper triangular matrix, then M is a diagonalizable over R. Next, if A and B are diagonalizable over R, then M is diagonalizable over R. If A and B are diagonalizable over R, then there exists lambda belongs to R such that M equals to I lambda 2. Option D, there exists lambda belongs to R such that M square equals to lambda I2. Now we are going to solve this problem. We have to check option A. For that, we choose a matrix. Let A equals to 1, 2, 0, 1 and another matrix B, that is 1, 3, 0, 2. These two matrices are upper triangular matrix. These two matrices are upper triangular matrix. Now we find out AB. What is AB? 1, 2, 0, 1 and 1, 3, 0, 2. Multiplying this, we get 1, 0, 7, 2. And BA. What is BA? B equals to 1, 3, 0, 2 and A equals to 1, 2, 0, 1. Multiplying this, we get 1, 5, 0, 2. Now we calculate M. What is M? M equals to AB minus BA. Therefore, AB is that 1702 minus 1502. So therefore, we get 0200. Hence, we can find. Hence, we can get M has eigenvalue. M has eigenvalue 0 and 0 has 1 independent eigenvector. Therefore, it is not diagonalizable. Here we get 0 is the one eigenvalue and 0 has only one independent eigenvector. Therefore, we cannot say the diagonalizable of AB. Okay. Now Now we check option B and C. For this, we consider let A equals to 1 0 0 minus 1 and B equals to 0 1 1 0. And option B is A and B are diagonalizable over R. Then we have to prove or give a counterexample that M is diagonalizable over R. Now we consider A and B matrix, that these two matrices are diagonalizable because eigenvalue of A 1 and minus 1, eigenvalue of B are 1, also 1 and minus 1. Therefore, we can say that A and B are two diagonalizable matrix over R, diagonalizable over R because distinct eigenvalue, and we can written as a product of linear factor, distinct product of linear factor. So A and B are diagonalizable. Now we have to prove M equals to AB minus BA diagonalizable or not. For that, we get AB equals to 1 0 0 minus 1 and 0 1 1 0. Therefore, we get multiplying these two matrices, we get 0 1 minus 1 0. And similarly, BA equals to 0 1 1 0 and 1 0 0 minus 1. Multiplying, we get 0 minus 1 1 0. Now M equals to AB minus BA, that is AB equals to 0 1 minus 1 0 and 0 minus 1 1 0. Therefore, this equals to 0 2 minus 2 0. Now characteristic equation of M is det of minus lambda 2 minus 2 minus lambda equals to 0. That means lambda square plus 4 equals to 0. Therefore, lambda equals to plus minus 2i. Eigenvalue of M are plus 2i and minus 2i. But these two eigenvalue belongs to C but not R. And clearly we can say that M does not lambda I2, and this M does not written as lambda I2 for any lambda. Therefore, we can say that A and B are diagonalizable over R, M is diagonalizable over R. This is false because M we give this matrix and eigenvalue of this M are plus 2i and minus 2i. which is belongs to C. But question is that M is diagonalizable over R. Secondly, and option C, if A are diagonalizable over R, then there exists lambda belongs to R such that M equals to lambda I2. This is also false because A and B are diagonalizable over R. Then there exists, we cannot find lambda belongs to R such that M equals to lambda 2. This is also false. That is, we get M not equals to lambda I2. And we have to check option D. What is option D? There exists lambda belongs to R such that M square equals to lambda I2. M equals to AB minus BA. Therefore, trace of M equals to trace of BA minus AB minus BA. This is trace of AB minus trace of BA equals to 0. For any 2 by 2 matrix M, characteristic equation is x square minus trace of M plus date of M equals to 0. From this we get x square equals to x minus date of M, that is lambda I2, and we can substitute trace of M equals to 0. Since A and B have real values. A and B are real values. Therefore, M also real values. So, date of M also real number. So we can take minus date of lambda equals to minus date of M, and this belongs to R. Therefore, we can get M square equals to lambda I2. M square equals to lambda I2. By Cayley-Hamilton theorem, every square matrix satisfies its characteristic equation. So M is a square matrix, it satisfies its characteristic equation. Therefore, M square equals to lambda I2. So option D is necessarily true. What is the matrix? Matrix is 0, 0, 0, 1, 1, 0, 0, 0, 1, 0, and B is 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. What are the options? Both A and B are diagonalizable over R. Both A and B are diagonalizable over R. Option B, A is diagonalizable over C but not over R. Neither A nor B is diagonalizable over R, but both A and B are diagonalizable over C. And option D is neither A nor B is diagonalizable over R. First, characteristic equation of A, that is A minus lambda of I equals to 0. Therefore, minus lambda 0, 1. 1 minus lambda, 0, 0, 1 minus lambda equals to 0. Expanding this determinant, we get lambda to the power 3 minus 1 equals to 0. That is lambda minus 1 into lambda square plus lambda plus 1 equals to 0. Product of these two factor equals to 0. Therefore, lambda equals to 1 and lambda equals to minus I plus minus root 3 I by 2. Therefore, eigenvalues of A are 1 omega square. Here omega and omega square belongs to C, but 1 is real. Therefore, all three eigenvalues are distinct. All three eigenvalues are distinct. Therefore, we can say that A is diagonalizable over C, but not over R. This is diagonalizable over C because of we can get distinct eigenvalues. Therefore, you can say that A is diagonalizable over R, but not over C. So therefore, we can say that both A and B are diagonalizable over R. This is false because A is diagonalizable over C. So A option is false. A is diagonalizable over C but not over R. B is true. Option B is true. Now we calculate the characteristic equation of B, that is minus lambda 0 1 0 1 minus lambda 0 0 0 1 minus lambda 0 0 0 0 1 minus lambda equals to 0. That is 1 minus lambda into minus lambda 0 1 1 minus lambda 0 0 1 minus lambda equals to 0. This is determinant. This is the eigenvalue of this is the date of A minus lambda I. Therefore, we get 1 minus lambda into lambda to the power 3 minus 1 equals to 0. Therefore, we can get lambda equals to 1 comma 1 omega square. Their eigenvalues of matrix B. Here 1 a repeated root. So the eigenvalues of B are this. Here omega and omega square also belongs to C. Now B is diagonalizable. B is diagonalizable over C or not because of repeated root. So algebraic multiplicity of 1 is 2. Now we have to find out geometric multiplicity of 1, that is n minus r of rank of b minus I, b minus lambda I, b minus lambda here lambda equals to 1, therefore b minus I. We get rank of b minus I, that is minus 1 0 1 0 1 minus 1 0 0 0 1 minus 1 0 0 0 0 0. So we get R3 equals to R3 plus R2 plus R1 minus 1 0 1 0 and 1 minus 1 0 0 and 0 0 0 0 0 0 0 0. Therefore, here rank of B minus A is 2. This is non-zero row, non-zero row. Therefore, rank of B minus A is 2. Therefore, B minus 2 equals to 2. That is algebraic multiplicity of 1. Therefore, we can say that algebraic multiplicity and algebraic multiplicity is same. Therefore, B is diagonalizable over C. So question is that neither A nor B is diagonalizable over R. So B is diagonalizable over C. B is diagonalizable over C and A is also diagonalizable over C. Both A and B are diagonalizable over C. Therefore, option D false. Thank you for watching my video. If you enjoyed learning mathematics in a simple and systematic way, don't forget like, comment and subscribe to MathX channel. Thank you.